I want to speak about it's a circle of ideas and questions on results. And I'm never really sure whether these are complicated questions, so maybe just approaching them with a completely different angle, you might find easier answers or easy constructions. So anyway, there are lots of open questions. So the title is Maximal discrete subgroups of unitary groups. Of operator algebras. And I mean, so there are, of course, a few definitions that I have to give you, but the idea is really to generalize some questions that have been around for a very long time in the finite dimensional setting and have also, I mean, found lots of interesting and beautiful applications and solutions. And so maybe the easiest case where you have encountered a phenomenon like this maximal discreteness is in the study of crystallographic groups. And so you have probably seen this if you have the isometry group of R square, then there are, I mean, of course, there are the translations, and there are the rotations, and there are the reflections. And if you fix some lattice, so for example, you are fixing a lattice like this, where you have an equilateral triangle, then there are more symmetries that are preserved by this geometric picture. For example, you can add another symmetry that would rotate the whole picture by pi divided by 3, and then you can also add a reflection. And if you add all these finitely many more elements, then you will suddenly obtain a group gamma, which contains this co-compact subgroup, and it cannot be enlarged anymore without making it non-discrete. So as soon as you add any more elements to it, you will certainly you will generate some limit points, and it's not discrete anymore. Right, and so the maximal discrete subgroups of the isometry group, these are the crystallographic groups. They have been classified. It's a beautiful story. Of course, that's a non-compact group, but in a similar way, if you have SO3, maximal discrete groups are like finite, of course. But it's also a very interesting story, and this is related to the classification of Platonic solids. And the finite groups, in fact, can be listed. So there's the biggest one is not the biggest one. So the important one is the symmetric group on 4 elements. So this is the symmetry group of the cube. Then there's the alternating group of 5 elements. That's the symmetry group of the dodecahedron. Right, and then if you look at this example, it's also interesting that there is another source of subgroups, which are the dihedral groups. So D2n. So these are the groups that have some preferred axis, and then they rotate in the plane perpendicular to the axis. And there's an angle here which is 2 pi divided by n. So this is an element of this group. And then there's also another element that would kind of flip the two sides. And then maybe also, well, maybe then it's not maybe then it's just a orthogonal transformation. Well, anyway, I mean, this is a group with 2n elements. You can also find it in SO3. And this group has the property that it is contained in, let's say, for example, D4n and D8n, and so on, by just adding more and more smaller and smaller angles here that would give you more rotations, but you don't change this flipping of the z-axis, right? And so you see, if you take the increasing union here, again you get a group that becomes denser and denser. So that is not, I mean, for example, this one already is, I mean, even for n, let's say even to 1, is no longer contained in a maximal discrete subgroup, because you can enlarge it more and more, whereas this one is maximal discrete. And so there is the group, I mean, the one case which is really peculiar is the case D4. So that's already a group that acts irreducibly here, so, and but it's contained in a maximal discrete subgroup, but it's also contained in this chain, so it can kind of choose into which side it goes, either in one where there's an end, right, or it goes in the other direction where there's no end, where things become more and more complicated. And so you see in this particular example that there's kind of a non-discreteness coming from a phenomenon that is essentially abelian, right? It's just these rotations that stay in one plane. And that's a general phenomenon. So there's a theorem due to Jordan and Schur, which says the following: if you have G in UN discrete or finite, so that's differently for all n there exists an n, so that if G in UN is finite, then there exists H in G normal, well, doesn't really matter, abelian anyway, a subgroup, and the index of H in G is bounded by this number n. Right, so there is some uniform maximal size of the non-abelian phenomenon that you can see, and all the rest in which it potentially may become non-discrete or like accumulate in some way. This is all due to abelian subgroups, right? So in some sense it's, well, not interesting in some sense from, well, a non-commutative point of view, certainly. Right, and so that's something that, and one can also say what this m is. So this has been actually computed, the best possible m, and it's very deep using classification of finite simple groups. This m as a function of n can be taken to be n plus 1 factorial. So you can take the, right, you have the symmetry group of n plus 1 elements that acts, well, has a very useful representation of one dimension less, and that's kind of the worst possible case. So everything else is simpler than that. Right, but still giving, for example, a complete list of the maximal finite subgroups is completely impossible, right? So because you don't even understand the groups that appear, right? Not to speak of exactly how they sit inside UN. So in some sense, well, if you do representation theory of finite groups, it's really an absolutely beautiful theory. You start with a finite group, and then you can essentially, with a nice theory, write down the representations of the group. If you start with the inverse question, you fix your unitary group when you want to describe the finite subgroups. That's almost impossible, right? So we make enormous progress because we ask the right questions and not the ones that we cannot answer because they have wild behavior in some sense. And so what I would like to address is basically the question: what happens if this UN here is replaced by a unitary group of a type 2-1 factor, right? And I'm looking at a particular situation where we, well, also have group for Neumann algebras, and we study the question, I mean, are the groups sitting in the unitary groups, are these, for example, maximal discrete? So let me write down the definitions. So question: what about p.m. For a 2-1 factor 2-1 factor n, where PUM is the unitary group modulo all the multiples of the identity element, right? Because you can always add, I don't know, more and more rational multiples of 1, and then it will not be a discrete subgroup as you make the angle smaller and smaller. But if you divide out this source of non-discreteness, it's an interesting question whether there exist maximal discrete subgroups in PUM. And in fact, it's an interesting question whether there exist discrete subgroups at all, right? So I will speak about this in a second. But first of all, before we come to some of the results or the ideas, I have to also tell you the metric. And so the metric is induced from the 2 norm, and so on UN we consider well, just the usual 2 norm. And with PUN we just take the quotient metric. And on PUN we define U, let me put a bar here. So right, U alright, so we just have this quotient metric. And most of the time I will actually just use a length function, right? So this is defined to be just the distance to the neutral element, right? And so we say that I mean, not just in this setting, but in the setting of metric groups, just to put this definition on the board, we say that gamma in PUM is discrete by definition if the inf over all length of non-trivial elements in gamma, if this is strictly positive, right? So you cannot converge to the identity element, and then gamma is called maximal discrete by definition if gamma contained in lambda and lambda is discrete implies that gamma is equal to lambda, so it's maximal among discrete subgroups. And well, sometimes we don't know whether if gamma is discrete, but we know something about all the groups, all the discrete groups that are contained, that contain gamma. And in this setting, so there's one more notion that I want to introduce. So the class of groups containing gamma, so the class of discrete groups containing, discrete subgroups of PUM containing gamma is called uniformly discrete. Well, if it is uniformly discrete, if this infimum is uniformly bounded away over all the groups, right? Uniformly discrete if the infimum well, this infimum, I mean, this is the infimum for u in lambda, u different from the identity, but now also the infimum over all the lambdas, which are still discrete, if this is still positive, right? So exactly this phenomenon here is not allowed, right? That you find bigger and bigger groups that kind of, if you take the union, converge for it. I mean, have limit points. For example, the identity is a limit point, but here I'm not even assuming that these groups are contained in one another, though it could just be groups sitting completely independently. And still you would say that they're uniformly discrete if one is not a limit point of a sequence of elements taken from these groups. And so there's one simple observation. If you are able to prove that the class of groups containing gamma is uniformly discrete, then you can add elements kind of step by step, and at one point you have to stop because you cannot add anything anymore. And any such group will be contained in a maximal discrete subgroup just by Zorn's lemma, basically. So let me call this condition a star. This implies that this star implies that gamma is contained in a maximal discrete subgroup. And this is exactly how, in some cases, we can prove the existence of maximal discrete subgroups. All right. Containing in particular
Andreas,
yes.
You said that it's even an interesting question to ask if there is some discrete subgroup.
Yeah, I will come to this point a little bit later because that's just pure speculation. Of course, there's one source of discrete subgroups that exists. I will. Let me just tell you the theorem. If gamma is mixed, I will define this later, mixed identity free, we will abbreviate this by myth. Then you have gamma sitting in the projective unitary group of the group for Neumann algebra of gamma, and this will satisfy star. Right, so, and that's a discrete subgroup, right? But it's somehow, it's very discrete in the sense that the distances are really maximal. And I think there are no cases where you have a discrete subgroup which is not, in this sense, maximal for non-trivial reasons. I mean, of course, you can add a projection and then it's sitting only in the corner, but if you wanted to generate it for Neumann algebra, I don't think there's an example of a discrete subgroup. Is that right? I don't think there's an example of a discrete subgroup that would not be of this form. All right. So, yeah. Any more definitions that are needed? Certainly this mixed identity free. But let me also mention my co-authors. So this is joined with Vadim Alekseev. And some data results are also joined with Alessandro Carderi and Robin Tucker-Drop. But that's not on the for-down algebra setting, but more on the setting of full groups. That's also an interesting situation where you can ask exactly the same questions. Right. And so, what is I should give you the definition. What is mixed identity free? So, that W be an element in the free product of gamma with Z. Then this W it induces a map from gamma to gamma just by evaluation. And so so there's this additional variable t here, right? So let's say this is generated by t. So we could basically write W of t because it's some verb that involves also the t, and apart from this, the constants coming from the group gamma. And so now if you have an element in gamma, you can just insert it for the t and compute the product in gamma. That gives you an element from gamma, and well, there's hardly anything that I can write to define this. I can just write W of g is defined to be W of g because you replace t by g, but I think I know what you know what I mean. I hope. Okay, so it's like the tautological map. What? Any questions?
No, I would just say, otherwise the definition won't help. You were saying, I guess you understand what I mean.
Well, I mean, I said I think I told you what I mean. Yeah, so I think that's the. So I really want to identify this element with the map. So we don't want to really make a difference. All right. So you have the map, and so gamma is mixed identity free by definition if and only if for all W different from the identity element in this great product, the map from gamma to gamma is non-trivial. Right? So there exists some element in gamma that will map to not the identity element. Or let's say non-trivial. In this setting, I have to say non-constant, right? Okay, I mean, one can normalize these maps so that they map the identity to the identity, then non-trivial would be the right thing, but okay, so the way I defined it, I just want any of these maps to be non-constant. All right. And so why is it called mixed identity free? Well, if this is not the case, then there exists some W which satisfies that this is, let's say, the trivial map, mapping everything to the usual element. And then this is like an identity for the group. So it's like a universal equation that is always satisfied, whatever you plug in, right? And that happens, I mean, for example, if you have a center, then you can take your constant to be from the center, and your element would be the commutator with this element, and that's because of the definition of the center. That's a trivial map that you're obtaining. And there are slightly more sophisticated constructions. So if, let's say, let me repeat it, gamma from the center and W of t is equal to the commutator, right? Okay, this is an identity, a mixed identity. It would be an identity if it wouldn't involve, well, that doesn't really make sense at the moment. I mean, first of all, you can say, why just one variable? And in this case, it really doesn't matter. So you can, if you have a mixed identity in many variables, you always have one in one variable. And then you can maybe ask, why is it called mixed identity? Well, that's because these constants appear inside the expression. So if I just say identity, typically in many variables, then it wouldn't involve any of these constants. That's the only difference. And that's a much, much more restrictive condition. So many groups, even though they had a center, they wouldn't satisfy any identity. But if they have a center, they satisfy a mixed identity for rather trivial reasons. And another example is that if you have a product of groups, then if you take a commutator with an element in the first factor, I mean, let's say A is an element of the form A, 1, right? So then this will only, I mean, the only thing that survives, the only part of G that survives is the part in the first factor, right? Because the B is not involved. And then if you take a commutator with B, then this is also the trivial map. So if you have a product of two groups, that's also a group that has a mixed identity, again, for reasons not so complicated. If you have finite, yes?
So again, you said that just having one letter is not a thing. You can have many letters.
Yeah. Mm-hmm.
Okay.
That's a little.
But it makes a difference, right?
Well, yes, of course. I mean, for the definition, a priori it makes a difference. But then there's a lemma showing that if you have a mixed identity in n letters, you find one in one letter.
You can substitute some
constants
for all the other ones.
Yeah, sure.
But you have to write it down. It's more complicated than these one-line arguments. What is interesting, if you have a finite conjugacy class, then also there's a mixed identity, because right, if you have G, C, G inverse, well, if C is finite conjugacy class, then, well, this conjugate can only take finitely many values. And so there's a little trick. Well, if you enumerate this conjugacy class, if you say C is equal to W1 through Wn, if that's your conjugacy class, then, well, for at least one of these i's, this will be trivial, right? You don't know which, a priori. But then you can start taking iterated commutator of these finitely many expressions. And since the commutator has, let me write, for example, in this simple case, right, if you look at this expression, then you already see it's enough that one of the two is trivial, right? And then you can iterate this to incorporate even more elements. And the only thing that you have to make sure is that in the end, the expression you're getting is not trivial in the free product, but that's usually easy. And to get a trivial as a map is really just relying on the fact that at least one of these things that go into the iterated commutator is trivial. So there are tons of little examples where you find mixed identities. Then it's I mean, one more example which is really surprising, I find it really surprising, is that SP2NZ, so this group, even though it's has no center, it's not a product, no finite conjugacy classes, this has also a mixed identity. It's more complicated to write down. And non-examples would include the free group on food generators, PSL, and Z, and, well, many other groups that you know, hyperbolic groups, for example, torsion-free hyperbolic groups.
What about solvable groups?
Well, they even satisfy identity, so they also satisfy a mixed identity.
Oh, yeah.
But it's an identity, I mean, there's a little argument, it's an identity in many variables.
Yes, but
I would first have to tell you to prove how you construct a mixed identity in one variable. This has to involve the mixed in an essential way.
I mean, can't you, like what you're saying, can you just fix some letter and then just...
Yeah, so if you have an identity, let's say in two variables, what you would do is, what you can do, for example, is to take G1, T, G2, G3, G4, and then you have all the freedom to choose G1, G2, G3, and G4. It will still be trivial, and that's enough freedom to ensure that this is non-trivial. So that's, I mean, that is a little bit more complicated because you really have to prove it's non-trivial. Okay. All right. I was looking for the other side. And one way of saying that the group is mixed identity free is, so the, following are equivalent. So one, gamma is mixed identity free, and the second, you will probably like this condition. So there exists Gn sequence in gamma such that L of gamma, a free product L of Z, and that's in the algebra power of gamma, like trace preserving, where this T is mapped to the unitary and represented by this sequence. Right? So there are no identities and so on. I mean, it needs a little bit of proof because here we really for one element in gamma free product Z, you find some G which witnesses that this is non-trivial, but now you kind of have to do this in a like better and better way, witnessing with a whole sequence that none of these W's are non-trivial, and so you have to come up with better and better elements in that sequence that eventually witness all the W's, right? So this is kind of the idea. But again, you can do this using iterated commutators, finding G's that work for a finite set of W's. So it's the same trick that we have seen already. All right, and so that's kind of useful because, first of all, you have this embedding, and then you have the sequence of elements that you can use to go back to the unitary group of the group for Neumann. Yes?
Can I ask a question? So, if you just look at the group case, just the fix some ultra filter on the natural numbers and take the algebraic ultra product.
Yes.
Then not having a free subgroup is equivalent to not having any identity. But in this case, for the mixed identity, what does it say about?
So there's a third condition saying that gamma free product embeds into like this. What do there exists? Right, so now the generator has to map somewhere, so it's automatically such a sequence.
But is it just any embedding, or do you really want it to be the diagonal on the gamma?
Well, I wanted to, sorry, I should have said this. So this should be the right embedding on that. In both cases, the group goes to the diagonal. So it's really an extension of the embedding that you already have. All right. Okay, so now how do you prove this theorem? Well, you have to find a mechanism that tells you that, you want to prove it's all the groups containing gamma are uniformly discrete. So whenever we basically add one element so that the resulting group is still discrete, we have to prove it's discrete with a uniform bound, right? Or in a different way, we can say if we add an element that is sufficiently close to the identity, then we have to be able to construct an entire sequence that converges to the identity. So as soon as we break this uniform bound that we want to exist, we have to be able to construct a sequence that converges to the identity. And so usually in the finite dimensional approaches and also, let's say in the C-star algebra version of this type of questions, this is done with the usual trick due to Zassenhaus, so I will tell you also the usual trick. And the usual trick is the following: if you want to compute the norm of 1 minus UV U star V star, then you can relate this to the linear commutator because this is the same as the norm of VU minus UV. But for the linear commutator, in each of the variables, you can add stuff that commutes anyway with everything else. So this is the same as the commutator of 1 minus V, 1 minus U minus 1 minus U, 1 minus V. Right, so there are a few minus signs that cancel. But apart from this, I have just added an element on each side of the commutator that commutes with everything, so that didn't change the expression at all. But now this is less than 2 times the norm of 1 minus U times 1 minus V. Right, so that's well, some computation. And what does it tell you? Well, it tells you if you have 2 elements that are already close to the identity, then the commutator will be even closer, right? Because if this is, let's say, less than epsilon, and this is less than epsilon, then the whole expression will be less than 2 epsilon squared, will be usually much smaller than epsilon, right? And then, of course, there are, and that's sort of the basic contraction mechanism that is used to, for example, prove the Jordan-Shor theorem. Because it tells you that as soon as you are kind of close to the identity, this can only happen because you run into something abelian, right? Or trivial, right? I mean, abelian includes trivial. Right? That's basically the key technical estimate, or just a simple computation, that is used in the proof of the Jordan-Shor theorem, and it works just the same way for C-star algebra, say, telling you that, well, as soon as you have sufficiently small elements, you either have relations or you converge to the identity using just iterated commutators. So now, unfortunately, in the von Neumann algebra setting, we are not working with a submultiplicative norm, but we're working with the 2 norm. And in general, there are small subgroups, right? You could just have a proof that is sitting on a very small projection. Right, if a Neumann algebra that's sitting in the corner of a bigger one, and then all the elements would have a small distance to the, or the unitaries would have a small distance to the neutral element, and well, and there's no reason why anything would contract towards the neutral element. But the new trick uses freeness in the phenomenon, in the free probability sense, but just sort of in a very modest form. So they told me that I should not call this free probability because it's obvious. So I will call it non-commutative probability or whatever. So anyway, so if
or probability.
So if you have just a 2-1 factor and you have U and V in the unitary group of n, which are free. So I mean, over the center, of course, right? So they have these elements. They do have a trace, right? The trace is important in just measuring their distance to the identity. But if they are free, then you can using non-commutative probability, compute exactly what is the distance of the commutator to the neutral element, right? Then the trace of u, v, u star, v star can be computed as 1 minus the trace of u, absolute value squared, 1 minus the trace of v, absolute value squared. And using this estimate, right, so remember that the length function that we are using is just the 2 norm, so it's essentially some function of the trace. So it's just measuring how far away is the trace from the identity, essentially maybe with a factor or with a square root. And you see now this phenomenon again, if you have, right, I could put, sorry, the 1 minus on this side. If you're interested in how close is this to the identity, then you're now getting a much better estimate. You're now getting a quadratic estimate that helps you to contract towards the identity. As soon as you have made, have ensured in addition that these two unitaries not only are they already close to identity, but they have to be free with respect to each other. Okay, and so how do we make them free? Well, we make them free. First of all, we can make them free in the ultra product, because there is an additional copy that is free. So if you let me write this on the next board. So if you have u close to 1 in pu L gamma, well, then what you do is to consider basically the commutator of u, gn u, gn star for n large enough. Right, and so in the ultra product, this sequence of GNs was free from the algebra diagonal copy of L gamma, and so these two, U and the conjugate of U, they will be mutually free in the ultra product, and then you can go back just a little bit in the sequence for n very large enough, n large enough, and then this element is non-trivial and closer to 1. So that's essentially the argument, of course. Oops, okay. There are more details that one has to add. All right. Okay, so that's that's basically the argument, and there are lots of interesting open questions. And so maybe the most easiest, the most interesting question that I can formulate is the question whether this group, it's mixed identity free, so it's contained in the maximal discrete subgroup. It's even all the discrete subgroups are uniformly discrete, so that's the consequence of what I just said. And the question is this maximally discrete? So any unitary you add, will it generate a group that accumulates at the neutral element? Yeah, we tried for some of the unitaries, but it's, yeah. For example, I thought that if you have a unitary in this radial direction, for example, then the free probability should be strong enough to answer this question whether the generated subgroup is still free. No, still discrete, sorry. But anyway, you have to do a computation for all the possible relations that this unitary could satisfy. Kind of complicated. All right. And so I have, what is it? We have 10 minutes or maybe 5 minutes left? 4 minutes?
Yeah, about 5 minutes.
About 5 minutes. So we also looked at this question for full groups of equivalence relations, and this is now joined with Vadim, Alekseev, Alessandro, Carderi, Vadim, drop, and so there you have a similar situation. So you have a group gamma acting on a probability measure space, and then your group that you are looking at is not, well, the unitary group, it's just the full group of the equivalence relation that is induced by this action. Right, this is again a group, well, this is, I mean, you probably have seen it before, it's kind of piecewise given by elements from gamma, and there's a natural length function that's just defined to be the measure of the support of G, where the support of G is the set of elements where G acts non-trivially. Right. The measure of the fixed point, etc., or the measure of the support. Yes, exactly. And so the question is, again, same question. I mean, first of all, maybe the group gamma is itself sitting in here already maximal discrete, or maybe more modestly, we can at least prove that it's contained in a maximal discrete group using the same strategy, but so here it's getting more complicated. So there are examples. So one is that gamma acts on its profinite completion with the Haar measure. So let's assume gamma is residually finite. So if gamma acts on its profinite completion, then, well, you can always basically enlarge this group in a canonical way by allowing all the partial self maps up to some index. Right, so I have to write down the formula, but it's kind of just adding permutations, but only up to a certain index. That would still be a discrete group inside the full group. And the union would in fact be a dense subgroup in the full group of the equivalence relation. And so this is not does not satisfy star, but our theorem is that if gamma is strongly mixing, then this inclusion in the full group satisfies star. And in addition, we have to assume again that gamma is mixed identity free. So the proof is quite different somehow. We haven't yet found a common denominator, like for example this type of alpha product embedding. But I don't know if I have time to tell you any of which will not the time to tell you anything of the proof. And certainly it also kind of leaves open what is under weaker mixing conditions, just weak mixing. So what happens in this situation? And I would believe that that's kind of still true, but kind of the details are more messy. I haven't fixed it. I haven't found it out yet. Okay, yeah, thank you for your attention.